Oxidation reduction reactions, or redox reactions, tend to be fairly complicated, and it's very tricky to predict the products of a redox reaction. And therefore, what we are going to do is to talk about how we might balance a redox reaction, knowing the reactants and the products. There are several different ways to go about balancing redox reactions. And in this video, I am going to talk about one particular way using half reactions. So we're going to go through a series of steps that will allow us to balance any redox reaction using this particular method. The first step in balancing this redox equation is to get rid of spectator ions. So I'm going to write the ionic equation and then ignore things that aren't changing oxidation state. So iron nitrate is an aqueous ionic compound. Silver nitrate is an aqueous ionic compound. This iron nitrate, iron 3 nitrate, is also an aqueous ionic compound, and so they're going to break apart into their constituent ions. So I'm going to write them as the ions. So we have iron, and in this case it's 2+ because each nitrate is 1-, and there are 2 nitrates with that. And I'm going to have a silver plus. I know it's silver plus because it's with 1 nitrate, and nitrate is -1. And that is going to form iron. This iron is 3+ because it is combined with 3 nitrates, each of which is -1. And then I have silver in its elemental state with a 0 oxidation state. So I can see that the iron has changed oxidation state and the silver has changed oxidation state or charge. However, the nitrates have all remained the same, and so I'm going to cross them out and not worry about them for the rest of the balancing of this equation. The next step is to assign oxidation states or charges to the elements that are left. In this case, it's fairly easy because once I write the ionic equation, I already know that my iron on the reactant side is 2+, and my silver on the reactant side is +1, and that my iron on the product side is 3+, and my silver on the product side is 0. Once I have the oxidation states assigned, I can figure out which element is reduced and which element is oxidized. In this case, the iron is oxidized, it's increased in charge from 2+ to 3+, and the silver is reduced because it's decreased in charge from + to 0. The third step is to write an oxidation and a reduction half reaction. So to do this, I take the element that is oxidized and I just look at the element that's oxidized and I write a reaction for that, and then I write a reaction for the element that's reduced. So in other words, I'm splitting this full reaction up into 2 halves, one that just focuses on the oxidation and one that just focuses on the reduction. So my oxidation half reaction is iron 2+ goes to iron 3+. And my reduction half reaction is silver plus goes to silver 0. The next step is to balance the element that changes oxidation state, so iron in this case and silver in this case, in each of the respective half reactions. So in this case, they're already balanced because I have 1 iron on the reactant side and I have 1 iron on the product side, so I don't really have to do much. Same thing with the silver. I have 1 silver on the reactant side and 1 silver on the product side already, so that's already balanced. Step 5 is to balance any elements that aren't the one that's oxidized or reduced, so any other elements, without changing the coefficients that you've already put onto the elements that are oxidized or reduced. Now, in this case, we have no other elements, so we can skip step 5. Step 6 is to balance the charges by adding electrons as appropriate. Electrons are negatively charged, and so we can use them to make sure that the charges are balanced. So for this half reaction, we have a 2+ charge on this side, and we have a 3+ charge on this side. So we have an extra positive charge on the product side, meaning we'll need to add an electron on the product side. On this half reaction, we have a positive 1 charge on the reactant side and a 0 charge on the product side. So we're going to need to add an electron onto the reactant side to make sure that both sides have the same charge. So that's going to look like this. We have iron 2+ goes to iron 3+ plus an electron. And then we have silver plus an electron goes to silver 0 solid. In step 7, we're going to add our half reactions back together again in such a way that the electrons will cancel each other. So we have iron 2+ going to iron 3+ plus an electron, and we have silver plus an electron, making silver 0. So if we add these two things together, we can see that we have 1 electron on the reactant side here and 1 electron on the product side here. So we can just add these two things together and our electrons will cancel. And if we do that, we get iron 2+ plus silver plus goes to iron 3+ plus silver solid. And the very last step is to add the spectator ions back in if it's necessary. So you remember that we took nitrates out of this equation, so we'll put them back in. So we have iron nitrate aqueous plus silver nitrate aqueous forms iron 3 nitrate aqueous plus silver solid. And you'll notice that, in fact, the reaction was balanced as written, but this is an illustration of all the steps that we would need to go through to balance a redox equation. Let's do another example that's maybe a little bit more challenging. So we've got a cerium nitrate aqueous plus sodium oxalate aqueous becoming cerium 3 nitrate and CO2 gas. So let's just go through each of our steps and see what we get. So the cerium and the sodium oxalate compounds are all ionic compounds, and so we're going to write them as their ions. So we have cerium 4+ plus 4 nitrates plus 2 sodium plus C2O4 2- oxalate goes to cerium 3+ plus 3 nitrates plus CO2 gas. And I can't break up the CO2 because that's a covalent compound. From this, I can see that the cerium clearly has changed oxidation state. The nitrate has stayed the same, and there's no sodium over on the product side at the moment, so I'm going to suspect that that is also a spectator ion. So we can cross off the nitrates and the sodium and ignore them for the rest of this problem. The oxidation state of the cerium is obvious at this point. However, the oxidation state of the carbon is not necessarily obvious. So let's assign oxidation numbers to the carbons on the reactant side and on the product side. On the reactant side, we have 4 oxygens attached to 2 carbons. Each oxygen is -2, so that's a total of -8. And I need my overall charge to be -2, so I need a +6. So each of these carbons must be +3. So each of these carbons is +3. And on the product side, I have 2 oxygens attached to the carbon. Each oxygen is -2, so that's a total of -4. The whole thing is neutral. That means that this carbon must be +4. So it's the carbons that have changed oxidation state. So we have cerium being reduced from 4 to 3, and carbon being oxidized from 3 to 4. So let's just write that down. We've got cerium 4+ is being reduced to cerium 3+, and carbon 3+ is being oxidized to carbon 4+. Next we write the half reactions. So cerium is easy, it's just cerium 4+ goes to cerium 3+, and we'll balance it later. And then for the oxidation, we have oxalate 2- goes to CO2. And again, we'll balance that in the next step. So in the next step, we're going to balance the element that changes oxidation state. The cerium is already balanced. There's 1 cerium here and 1 cerium here. So we can just copy that down. Cerium 4+ goes to cerium 3+. However, for the oxidation half reaction, we have 2 carbons on the reactant side and only 1 carbon on the product side. And so we are going to need to multiply the CO2 by 2 to balance the carbons. The next step is to balance any other elements, and in the reduction half reaction there are no other elements, but in the oxidation half reaction I have to make sure the oxygens are balanced. So let's just copy our reduction half reaction down, because we don't need to do anything with that. And then let's inspect our oxidation half reaction. So we have 2 carbons, 4 oxygens, 1, 2, 3, 4. Each CO2 has 2, and we have 2 CO2, so we have a total of 4 oxygens on the product side. So actually, the oxygens are balanced already. So C2O4 2- goes to 2 CO2. The next thing is to balance the charge by adding electrons as appropriate. So for the reduction half reaction, we're going to need to add 1 electron to the cerium 4+ to make it cerium 3+, so that I have a total charge of +3 over here. 4+ -1 is 3+, and I have a total 3+ charge on the product side. And for the oxidation half reaction, I've got an extra 2- on the reactant side, so I'm going to need 2 electrons on the product side to balance that charge. So I have C2O4 2- oxalate goes to 2 CO2 plus 2 electrons. Now the last thing to do is to add the half reactions back together so that the electrons cancel. So when I do this, I am going to need to multiply this equation by 2, because I need to have 2 electrons on the reactant side to cancel the 2 electrons on the product side over here. But I can't just multiply the electrons, I have to multiply the whole thing. So if I multiply the electrons, I have to multiply the cerium to keep everything balanced. So I multiply the whole thing by 2, and then I add it to this one, and then the electrons will cancel. So when I do that, I have 2 cerium 4+ plus my oxalate goes to 2CO2 plus 2 cerium 3 plus. And my electrons have canceled, so once I've added the half reactions back together, I should have no electrons in my equation. The last step is to add the spectator ions back in as necessary. And so if we recall, our cerium had nitrates with it and our oxalate had sodiums with it. And so we're going to write 2 cerium nitrate plus sodium oxalate goes to 2CO2 plus 2 cerium nitrate. And to finish balancing this, we need to recognize that we have sodiums on this side of the equation and no sodiums on the product side. And we have a total of 8 nitrates on the reactant side and 6 nitrates on the product side. So we need 2 more nitrates on the product side and we need 2 sodiums on the product side. But that's really nice because if we just add 2 sodium nitrates into our products, we will end up with a balanced equation. So the thing to recognize is that when you have a skeletal equation that's unbalanced for a redox reaction, you may or may not have all the products or all the reactants listed, and you might need to add in some reactants or products in this case in order to balance it. But you can't use things that you don't already have in the equation, and so typically you're only adding in spectator ions to balance that equation.